شغل النور. Okay. بسم الله الرحمن الرحيم. I hope you can hear me. So we can begin the lecture today regarding the Laplace. So this will be the last lecture for this semester, inshallah ta'ala. There will be a homework regarding the Laplace. It is 5 marks, and I will send you, I think either today or tomorrow, and then you can um, solve that to get 5 marks, inshallah ta'ala. So I hope everybody can hear me. Okay, I'm just testing and then we can start. Okay, so I think everything is working. So yeah, so let us start. You can look at the lecture I sent you. So let us begin with the definition of the Laplace transform. Laplace transform. The Laplace transform is defined by x of s minus infinity to plus infinity, x of t e raised to the power minus st dt. And we can compare the Laplace transform with the Fourier. So the Fourier, if you remember, it was defined as minus infinity to plus infinity, x of t e raised to the power minus j omega t. So the difference between the Laplace and the Fourier is the instead of e raised to the power minus j omega t, we have e raised to the power minus st. And what is s? S is actually includes j omega. So s here is equal to sigma plus j omega. So in this way, the Fourier transform actually included in the Laplace transform. And we will see the relation between the two in a few minutes. Now let us do an example in which we have to find the Laplace of the function e raised to the power minus at u of t, as we did for the x of omega. So the Laplace will be equal to minus infinity to plus infinity, e raised to the power minus at u of t, e raised to the power minus st dt. Now I can combine the two exponentials and drop u of t. If I drop u of t, the limits will be from 0 to infinity, because this u of t is 0 for t is less than 0. So I can change the limits from 0 to infinity, and I can just at the same time add the two functions. So s plus a t going from 0 to infinity. Now when I put infinity here, this will go to 0, and when I put 0, it will go to 1. So it will be, and then minus 1, so it will be 1 over s plus a. So this is my Laplace transform. So I can write as we did for the Laplace, for the Fourier transform. I can also write the same relation, the same type of method. I can write the Laplace. Now, there is a relation between the Laplace and the Fourier, and that relation is because of this identity, that my s is equal to alpha sigma plus j omega. So let us first uh, uh, write down the Laplace, and then we can, so I can just delete this from here. So I can just leave the relation. So this is, so I have this relation here. Now, I also know this relation from my Fourier transform, that the Fourier transform of e raised to the power minus at u of t is 1 over a plus j omega, right? So this is, we know from our knowledge of Fourier transform. So now from this definition, let us put sigma plus j omega here. So this is equal to minus infinity to plus infinity x of t e raised to the power minus sigma plus j omega t dt. And this is equal to, I can split the two exponentials. So this will be x of t e raised to the power minus sigma t e raised to the power minus j omega t dt. Now I can see that this is the Fourier transform, right? This is my Fourier transform, exactly my Fourier transform, the definition of my Fourier transform. So which means that that x of s, this implies that x of s is the Fourier transform of x of t e raised to the power minus sigma t. So I can use all the formulas of Fourier transform by just replacing x of t by x of t e raised to the minus sigma t and then finding the Fourier transform. So let us do an example of this so that we know how to the relation between uh, the Fourier and the Laplace. So now the same example actually. So x of t is equal to e raised to the minus at u of t. Now x of t e raised to the minus sigma t is equal to e raised to the minus at e raised to the minus sigma t u of t, which is equal to e raised to the minus sigma plus a t u of t. Now I know the Laplace Fourier of this. So the Fourier of e raised to the power minus at u of t is 1 over a plus j omega. Now if my function is e raised to the minus a plus sigma, the only the only substitution I have to do is to replace a with a plus sigma. E raised to the minus at u of t, the Laplace is Fourier is 1 over a plus j omega. So if I change a to a plus sigma, then the simple uh, change will be a plus sigma plus j omega. Now, what is sigma plus j omega? What is sigma plus j omega? Sigma plus j omega is s. So, which means that this is equal to so e raised to the power minus a plus sigma t u of t. The Fourier transform is 1 over s plus a. So which is exactly what we said before, that the Fourier transform, the x of s is the Fourier transform of x of t e raised to the minus sigma t. So this is how the two transforms are related to each other. So if we know the Fourier transform, we can find the Laplace transform. If we know the Laplace, we can find the Fourier by just making sigma equal to 0. So if we make sigma equal to 0, x of s becomes x of omega. So this is so if we know the Fourier, I can find the Laplace. If we know the Laplace, I can find the Fourier. So if I make sigma equal to 0 here, it will be 1 over a plus j omega, which is the Fourier transform of e raised to the minus at u of t. Now the next topic is how to find the region of convergence. Yeah, so this is example number 3, the region of convergence. Now there is something which is different from the Fourier transform here in Laplace. The difference is the region of convergence. So in Fourier transform, we don't worry about the region of convergence. But in Laplace transform, we find the Laplace. So we have to find the Laplace transform, and we also have to find the region of convergence. Now, what is the region of convergence? Let us define it here. So what is the region of convergence? So the region of convergence, or ROC. ROC of the Laplace is, okay, just a second. I need to bring the power cable. There is no power here, so it will just give me 1 minute, please. Okay, sorry. So yeah. Okay. Now the region of convergence of Laplace transform is the region in which the Laplace does not go to infinity. And to find the region of convergence, we have to go back to the integral. So let us do an example in which I need to find the region of convergence of the same function. So I have x of t equal to e raised to minus at u of t. I need to find the Laplace, which is equal to minus infinity plus infinity, e raised to minus at u of t, e raised to minus st dt, which is equal to from 0 to infinity, e raised to minus s plus a dt, t dt, and this is equal to minus e raised to minus s plus a from 0 to infinity. Now, to find the region of convergence, I have to replace s by sigma plus j omega. So this is equal to minus, yeah, there is an s plus a here. So e raised to the power minus s, I just replace it by sigma plus j omega plus, sorry, in this example, I assume that a is 2 to make things more understandable. So I have it as 2. A is equal to 2 here because it will be a more realistic problem. So I have s sigma plus j omega plus 2, and this goes from 0 to infinity, and s plus a. Now, to put the limit, I put first infinity and then I put 0. So this is equal to minus 1 over s plus a, and so I have e raised to the power minus. Now I just want to I just replace these two with each other. So I have j omega plus sigma plus 2 infinity, and then minus e raised to the power 0, right? So now let's look at it this closely. If sigma plus is greater than 0, then e raised to the power minus all this goes to 0, right? Because then it will be, this will be minus infinity, and this will be going to 0. If sigma plus 2 is less than 0, then this is negative, and negative multiplied with negative is positive. Then this will go to e raised to the power plus infinity, and this will go to infinity. So this is, we don't want this. This is okay. So this means that the region of convergence, so this is how we define the region of convergence. Region of convergence is when sigma plus 2 is greater than 0, or sigma is greater than minus 2. And we also, because s is equal to sigma plus j omega, so sigma is real part of s. So we can also say that when the real part of s is greater than minus 2, then the Laplace transform, plus Laplace transform converges. That's why we call this the region of convergence. Now, how do we draw this region of convergence? We have to draw it. So we have to draw it in the a complex plane, as we draw when we draw the roots of a function. So for this, we need to first draw all the roots. Okay, now after all this, this comes out to be 1 over s plus 2, because a is 2. So this is my x of s, as I did before. So what are the roots of this equation? I put the roots here. It is minus 2. So the region of convergence is greater than minus 2. So the region of convergence is everything which is greater than minus 2. So this is region of convergence. Now let me draw this again to make the things clear. Let me just delete this here. So the region of convergence is drawn in the complex plane. So I have, this is my complex plane, this is the sigma axis, and this is the j omega axis. So first of all, I draw the roots, which is minus 2. So the region of convergence is greater than minus 2, which means that it is everything which is greater than minus 2 on this side. All right. Now, how to find the region of convergence? There are some rules which I will discuss next, and then I will give you another example, another 2 examples. So, yeah. So there are 3 rules basically, which is you can look at the lecture which I just sent you, and it is, I think, on the 3rd or 4th page. So what are the rules of region of convergence? The rules of region of convergence are very simple. There are 3 rules. So rule number 1 is when x of t is right-handed. So when x of t is right-handed, which means that it is open on this side, right side, like e raised to minus at u of t, right-handed. So for right-handed x of t, the region of convergence is right to the last pole. Rule number 2, for left-handed x of t, region of convergence is left to the last pole. So if this is the function, right-handed function, the region of convergence will be, so if there are 2 poles like this and this, so the region of convergence is right to the, then the region of convergence, and the poles are like this. The region of convergence are left to the pole. And the third rule is if the function is both left and right-handed. So if it is an open function like this, so if x of t is an open function, then the region of convergence is in between the poles. So the region of convergence is between the poles. So these are the 3 general rules, and using these rules we can find the region of convergence of any function. Now let us go to the example number 4, in which we have 2 roots. So we have 2 exponential functions, and we are looking at the summation. So yeah, these are the 3 rules. So let us look at the example number 4. Example 4, which says that x of t is equal to e raised to the power minus 2t u of t minus e raised to minus t u of t. So this is equal to, yeah, so I know the functions. So e raised to minus 2t u of t. I can go to the table which I sent you. So I can see from the table that the Laplace of e raised to minus 2t u of t is 1 over s plus 2, and the Laplace of e raised to minus t u of t is 1 over s plus 1. Now both of them are right-handed. This is right, and this is right. Why this is right-handed? Because I can draw the function. This is my e raised to minus 2t u of t, and this is my e raised to minus t u of t. So if both of them are right-handed, their sum is also right-handed. And the sum will be just another exponential and the summation of these two. So it will be another exponential, but like something higher than that. Okay, so both of them are right-handed. So my region of convergence will be like this. But I need to draw the two roots. So the second step is to draw the roots. So I can draw the roots here. So the total Laplace will be equal to 1 over s plus 2 minus 1 over s plus 1. Now in this, in the notes, there is, I put the positive sign, but it is actually the negative sign, right? Or, yeah, I can just know, this is plus actually, like that. So I have plus between. So there is a correction there in the question. You can change the negative to positive. So if I add the two, I will get s plus 1, s plus 2, and s plus 1 plus s plus 2. So this will be s plus 3 divided by s plus 1, s plus 2. So this is equal to 2s, 2 as a common factor, and s plus 3 by 2 divided by s plus 1 and s plus 2. Now I can draw the region of convergence. So I can draw all the roots. I can draw the poles and zeros. So we know that if the function of this kind, I have poles at s equal to minus 1 and minus 2, like that, and zeros s equal to minus 3 by 2. So poles are the roots of the functions for which the function will become infinity. So if I put s equal to minus 1, the function will become infinity. If I put s equal to minus 2, the function will become infinity. So these are the roots. So these are also called poles. Zeros are the numbers at which uh, the function becomes 0. So if I put minus 3 by 2, this will become 0, and the whole function will be 0. So I can draw these poles and zeros. So I have one at minus 1, and I have the second one at minus 2, and this one is in between. So this is 0, which is minus 3 by 2. Now what is the region of convergence? This is the function which opens towards right. So my region of convergence will be right from the last pole. So this is my region of convergence. Okay. Okay, now let's go to the example 5, and then we can just finish this lecture, and then I will give you the homework, and based on that you can solve these questions, which will be not much difficult. Uh, the full coverage when we are regular. So this is just an introduction. Now last example, example 5, is x of t equal to e raised to the power minus 2t u of t plus e raised to the power minus t cosine 3t u of t. Now this is simple, we do it many times. So this is just 1 over s plus 2. Now this one is, you have to look at the table, and from the table I can see that this is, if you look at the table which I sent you in the beginning of the lecture, so So in this table, the Laplace, there is Fourier transform and there is a Laplace transform at the end. This table is, by the way, on the website too. So if you look at number 9, I can write the Laplace of e raised to the power minus at cosine bt u of t, which is similar to that, and that is equal to s plus a divided by s plus a square plus b square. S plus a square plus b square. So I can apply this formula to calculate the Laplace transform. So e raised to the power, now a is 1. So I have e raised to the power minus t cosine 3t u of t will be s plus 1 divided by s plus 1 square plus b square. B is 3. So which is 9. Right? Now this is the Laplace, but I still need to find the region of convergence. So to find the region of convergence, I need to find the roots. So the roots of this equation are, so I need to find the roots of s plus 1 square plus 9, which is equal to s square plus 1 plus 2s plus 9, which is s square plus 2s plus 10. Now I can use the quadratic formula to find the roots. So the quadratic is 4 minus 4ac, so 10, so it will be 40 divided by 2a, which is 1, so this will be 2. So this is equal to, this is minus 36, so this will be 6j. This is an imaginary number. So the roots will be minus 2, and 2 divided by 2 is 1, so minus 1 plus minus j 3. So these are the roots. So I have 2 roots here and 1 0. The 0 is at s equal to minus 1. So I can draw this, the region of convergence here. So I have minus 1 plus j3. So this is, if this is minus 1 and this is, so this is j omega and this is sigma. So minus 1 plus j3, I have one root here, and minus 1, so this is minus 1 plus j3, and this is minus 1 minus j3, 2 roots, and the 0 is at minus 1. So there is a 0 here. And the region of convergence, because this is also towards right, this function is like this, e raised to the minus at and cosine. So this function is something like this. It is a cosine exponential. So it is a cosine function coming exponentially down. So this is towards right. So the region of convergence will be on the right hand side. All right. Now before I go, we can do one example in which the region of convergence is on the left side. Let me look at the example here. If I can find one example like that, we can just go through it. So Okay, so yeah, I have one example here in which let me call it example number 6. So yeah, so this is example 6 here. It's not in the notes, but I can just write it here. So x of t is equal to e to the power plus 2t u of t. Now this function is actually, sorry, this is u of minus t. All right. So this function is like this. It's going up, so it is like this, like this. Yeah, u of t. Sorry, u of t. So when there is a u of t here, so this will be like this. So it is like this function. So it is a function like this, and here it is. This is 0 because of u of t. So this is my e raised to the plus 2t u of t. So as we can see that it is opening towards left. So first of all, let us look at the Laplace. The Laplace from the formula, it is x of s is equal to 1 over, I can look at the table, and from the table it is like this, minus a, right, s plus a. So a is 2, so this will be e raised to the plus 2t. Yeah, no, this is s minus a. So a is minus 2 here. So it will be u of t 1 over s minus 2. And the reason is simple, that when we have e raised to minus 2t u of t, uh, the, the, the Laplace is s plus 2. When I have e raised to plus 2t u of t, then a is, yeah, this is s plus a, but a is less than 0. So a is minus 2. So this will be minus 2 here. So this is 1 over s minus 2. Now, what is the region of convergence? The region of convergence is I draw my root. So my root is here now, s equal to 2. And it is on the left side of this root. So this is my region of convergence. All right. And any question, you just apply the same rules. If it is left, then the region of convergence is left to the root. Now, I will not go through the circuit question, but it will be in the homework. But I just want to tell you that where we most of the time use Laplace. As you can, I mean, in electric engineering. In electric engineering, some people know that we use it in circuits too most of the time when we use circuits. When we when we have to find the solution of different circuits, especially when we have initial value problems. So if there is a simple circuit like this, for example, I have a battery, and this is, by the way, if you look at the uh, problem set, it is example number 9, problem 9 on problem set number 7. Now this problem set is not actually fully included in your course. The only problems which will be asked you in the final will be just what the problems which I give you in the homework. All right, from similar problems. You don't have to actually just look at the similar problems in the problem set, not all the problems. So in this question, I have inductance and a resistance and a capacitance. So I have L, R, and C. And this is 1 Henry. This is 2 ohm. and this is 1 over 5 farad. And uh, what happens is, before uh, the switch is on, this is first the switch is on, and there is a 5 ohm resistance here. So at t equal to 0, the switch is actually opened. So this is opened at t equal to 0. Now when the switch is on, the circuit is like this. This is an open circuit, right? Because this is a capacitance and the current will not flow. The current will flow like this. And the, the initial current on here will be, this is 10 volts. So 10 over 5. So the current here will be, and this is I naught. The current, initial current is 10 divided by 5, which is 2 ampere. Now when we open the circuit will look like this. So when we open the circuit, when we open the switch, the circuit will look like this. So the circuit will look like this. Then resistance and a capacitance, and this is 10 volts, and this is 1 Henry, 2 ohms, and 1 by 5 farad. And I have this current I naught equal to 2 ampere. Now, if you use the Fourier transform, this will not take into account the initial current, because the Laplace transform, it takes into account the initial current. So that's why we use Laplace transform. So what will be the voltage equation of this question? The voltage equation will be, this is 10 volts, so this is 10 u of t equal to voltage here. This voltage will be L d, I call the current Y. So I'm writing the voltage equation. Yeah. So I'm writing the voltage. So the voltage here will be voltage here. The voltage here, the voltage on a capacitor inductor is L dV by, sorry, L di by dt. So this is the current here. So the voltage, and voltage on VL, and VC is equal to 1 over C I dt. So I write all these equations. So my current is Y, so dy by dt, plus this is Ry of t, and plus 1 over C y of t dt. Okay, and then this is, I can put the values. This is 1, so this is dy by dt, plus 2y of t, plus 1 over 5, 1 over 1 over 5. So this is 5 y of t dt. So what I do, I find the Laplace transform. So what is the Laplace of the dy by dt? Now this is also in uh, the table. So if you go to the table, I can, if you go to the table, I can see the properties of Laplace, in which, so I can look at the table once again, and I can go to the last page, and I can look at the last page for the Laplace transform. So if my Laplace of my differential is s f of s minus f of 0. So which means that if I want to find the Laplace of a differential, it will be s multiplied by y of s minus the initial current, which is 2 amperes. So I can now go back to the problem, and I can find the Laplace of both sides. So the Laplace of uh, 10 u of t is just 1 over s. So it will be 10 over s equal to the Laplace of this is dy by dt. So it is s y of s minus the current, which is 2, initial current, or I of 0, and then plus 2y of t, which is 2y of s, and then minus 5. And similarly, the integral is also given there. Uh, the the Fourier transform of the integral is the Laplace transform of the integral is 1 over s f of s. So it will be plus 5 over s f of s. And then I will not go through the whole problem, but you can look at the problem set number 7. And what we do here is we just combine y of s. Sorry, this is y of s. We can combine the y of s and find y of s first, and then find y of t from the inverse Laplace transform. All right. So this question will be included in the homework, inshallah. Okay. So you can. It's not very difficult. Just follow the problem set number 7. It is the problem number 9, and you can find in the homework there will be a little bit change in the values, and that's it. All right. Okay, so thank you for attending the lecture and attending the signals and signal system course. I know that this we started good, but then the thing happened and we couldn't actually meet. So all what we were doing were communicating through the internet. But alhamdulillah, we try to do as much as we can. Uh, and this homework will be 5, and then I think then it will be done. There is one more homework, and then we'll be done by 80% of the marks, and then we will see that how can we do the final exam. All right, that will be remaining 20%. Now there is one thing remaining, the MATLAB, right? So please submit the MATLAB on time. I think it is due this Sunday. All right. So and then inshallah we will be done by and also submit the Laplace in the second homework, and then it will be the end of the semester work, which is 80% of the total marks. All right. Any question you can communicate with me on the WhatsApp. All right. Thank you. Assalamu alaikum.